Aircraft are marvels of engineering, yet even the most advanced machines occasionally fail. Behind every mechanical issue, every emergency landing, and every aviation accident lies a combination of physics, human decision-making, and environmental factors. For enthusiasts and engineers alike, understanding why aircraft fail is not about fear, it's about respecting the complexity of flight and appreciating the ingenuity that keeps planes aloft. From early piston trainers to modern jetliners, the causes of aircraft failure reveal patterns that have shaped aviation safety, design, and innovation. Failures in aviation are rarely caused by a single factor. Instead, they are usually the result of a cascade of events, mechanical, human, and environmental, that converge in critical moments. Even minor issues can escalate if systems aren't properly monitored or maintained. This understanding began in the earliest days of flight. Otto Lilienthal, the German pioneer who glided in the late 19th century, experienced multiple crashes during his experiments. His wooden and fabric gliders were structurally simple, yet even small miscalculations in wind or balance could lead to catastrophic results. Lilienthal's work, tragic as it sometimes was, highlighted the importance of careful testing, observation, and understanding of aerodynamics, principles that remain central to preventing failure today. The first powered flights by the Wright brothers in 1903 demonstrated not only that controlled flight was possible, but also that failure was a constant companion in aviation. Early aircraft were fragile, with limited understanding of stress on wings and control surfaces. Engine failure, structural weaknesses, and pilot error were common. Even a small mechanical defect could end a flight in seconds. As aviation evolved, engineers learned to anticipate these failures. Redundancy, stronger materials, and more reliable engines became essential. But history shows that as technology grows more advanced, the complexity of potential failure grows as well. World War I accelerated the pace of aviation, and with it, the stakes of failure. Aircraft were used as reconnaissance platforms and weapons, and any failure could cost lives. Early biplanes often suffered structural failures under combat stress. Wooden spars would crack, fabric covering would tear, and engines would overheat. Pilots learned to respect not just the enemy, but the limits of their own machines. Every design improvement, stronger engines, better propellers, and improved aerodynamics, was in part a response to the lessons of failure. Engineers realized that an aircraft could only be as safe as the weakest component in its design, and that even minor failures could cascade into catastrophic results. By the 1920s and 1930s, aviation had shifted into commercial service, but failure was still a constant concern. Early airliners like the Douglas DC-2 and Boeing 247 introduced metal airframes and more powerful engines, yet accidents continued due to engine failure, structural fatigue, and pilot error. Aviation enthusiasts studying this era often overlook one subtle factor: weather. Pilots in the early decades had limited instruments and navigational aids. Flying through clouds, storms, or turbulence could expose weaknesses in aircraft design. Even modern flight crews regard weather as one of the most significant risk factors for aircraft failure, reminding us that environmental conditions have always been critical. World War II produced some of the most robust and high-performance aircraft ever built, yet failure remained a central theme. The Rolls-Royce Merlin engine, which powered Spitfires and Lancasters, was revolutionary, but it demanded precise maintenance and monitoring. Improper lubrication, fuel contamination, or extreme temperature fluctuations could quickly result in engine seizure. The Kaufman starter, used to spin engines quickly in combat conditions, was ingenious, but also introduced a potential point of failure if not handled correctly. Wartime experience demonstrated a fundamental truth: even the most advanced design is only as reliable as its operation and maintenance. The jet age, starting in the late 1940s and 1950s, brought unprecedented challenges for aviation. Turbojet and turbofan engines operated at higher speeds and temperatures than piston engines, pushing materials and aerodynamics to their limits. Iconic aircraft like the Boeing 707, Douglas DC-8, and Boeing 747 opened mass commercial aviation, but also exposed vulnerabilities. Metal fatigue, once minor, became critical. The de Havilland Comet's mid-air breakups in the 1960s revealed how repeated pressurization cycles could create microscopic fuselage cracks, permanently changing aircraft design, testing, and inspection standards. Human factors remain central to aircraft failure. Pilot error, misreading instruments, poor decision-making under stress, or over-reliance on automation can turn minor issues into emergencies. Modern aircraft, like the Airbus A320 and Boeing 787, use advanced fly-by-wire and digital systems, which reduce some risks but introduce new complexities. Environmental hazards, turbulence, lightning, ice, volcanic ash, and microbursts also test aircraft limits, despite radar, de-icing, and weather systems. Maintenance and materials are equally crucial. Millions of components require meticulous inspection. Improper maintenance can have severe consequences. Advances in predictive maintenance and AI help, but attention to detail is vital. Material evolution, from wood to metal to composites, improved performance but added new failure risks. Understanding each material's behavior under stress and fatigue remains key to preventing accidents and ensuring safe flight. Engine technology deserves special attention. From radial engines in World War II fighters to turbofans in modern day, propulsion systems are both a source of power and potential failure. Engine failure can result from mechanical defects, fuel contamination, oil starvation, or overheating. In multi-engine aircraft, redundancy can prevent disaster, but in single-engine general aviation aircraft, engine failure is a critical emergency. Understanding these risks have shaped pilot training, emergency procedures, and aircraft design. Even in today's era of AI and autonomous systems, aircraft failure remains a key concern. AI supports predictive maintenance, flight optimization, and air traffic management, while electric aircraft like the Lilium Jet and Aviation Alice face challenges in battery performance, thermal control, and software reliability. Digital systems and automation reduce human error but introduce new potential failure points. History reveals patterns. Early flights struggled with lift and control. The jet age tested speed, altitude, and materials. Modern aviation balances automation, efficiency, and environmental responsibility. Failures drive progress. Accidents lead to improved design, stricter regulation, and enhanced safety. For content creators, these stories are rich material. Exploring incidents, near misses, and engineering solutions across manufacturers like Cessna, Beech, Kraft, Piper, Boeing, and Fokker shows how failures shaped the industry. Technical lessons from wooden wing stress to comet fuselage cracks and modern composite systems highlight the evolving interplay of technology, human oversight, and innovation, offering both dramatic storytelling and educational depth for enthusiasts, engineers, and investors worldwide. The aviation industry today is safer than ever, yet the lessons of failure remain critical. Regulatory agencies like the FAA and EASA enforce rigorous maintenance, certification, and operational standards. Airlines, general aviation operators, and manufacturers invest billions in safety technologies. Aircraft are now flying computers capable of self-monitoring hundreds of parameters. Yet, despite these advances, no aircraft is immune to failure. Understanding why failures occur helps pilots, engineers, and enthusiasts appreciate both the complexity and the achievement of modern flight. Looking ahead, the future of aviation failure prevention lies in AI, electrification, and predictive analytics. Hybrid and electric aircraft bring new propulsion challenges. Autonomous cargo drones and regional eVTOLs must be designed to fail safely. Advanced sensors and machine learning algorithms are now detecting issues before they manifest, allowing maintenance crews to intervene proactively. But as technology advances, the fundamental principle remains unchanged. Failure is not a sign of weakness, it is an opportunity to improve.
In conclusion, aircraft failure is as old as aviation itself. From Lilienthal's gliders to the latest electric and AI-assisted aircraft, the causes of failure have evolved, but the lessons remain. Mechanical defects, human error, environmental hazards, maintenance lapses, and material limitations all play a role. Aviation enthusiasts benefit from studying these failures because they reveal the engineering ingenuity, operational discipline, and continual learning that underpin every successful flight. Understanding why aircraft fail is not about fear, it's about respect. Respect for physics, for engineering, and for the skill of the pilots and maintenance crews who keep the skies safe. Aviation will always carry risk, but it is the relentless study of failure that transforms risk into innovation, danger into knowledge, and ambition into achievement. For enthusiasts, engineers, and pilots, these lessons are the heart of aviation, showing that behind every safe flight lies a history of challenges overcome, mistakes analyzed, and solutions engineered. Failure is not the enemy of flight, it is its teacher. And if history teaches us anything, it is that aviation never stops evolving. The failures of today will shape the aircraft of tomorrow. The lessons learned from past mistakes are embedded in every wing, every engine, and every cockpit. Understanding these truths makes every flight not just a journey through the sky, but a journey through a century of human ingenuity, perseverance, and respect for the power of flight.